Jen, I will start the recording now.
Okay.
Good afternoon, good morning, everybody. This is the first colloquia of this year, September, of the Instituto Astrofísica de Andalucía, and today we have the presence of Dr. Jana Kautz from the National Solar Observatory in Boulder, Colorado, United States, and she will talk about a new look at our star, the Daniel K. Inouye Solar Telescope. Jana will be make the introduction by Isabel Marquez, our PI of the Severo Ochoa program. Please, Isabel.
Thank you, Rene. Hello, everybody. Thank you very much for being here again after the summer break. That I hope that you could profit of it and all the good wishes you have been accomplished during this time. And we are back again with our strengths. And I'm especially grateful to Gianna Kautz, who accepted our invitation for this first web colloquium of the Severo Ochoa project at the Institute after the summer break. So thank you very much, Gianna Kautz. And so Gianna Kautz is associate scientist at the United States National Solar Observatory in Boulder in Colorado. She received her PhD from the University of Florence in Italy in 1993. And after a few years in the United States as a postdoc, she went back to Italy as a staff researcher at the INAF, at the Osservatorio Astrofisico di Arcetri in Florence, where she spent over 2 decades. And during this period, she was a co-investigator for the highly successful interferometric bidimensional spectrometer IBIS, a double Fabry-Perot system built in Arcetri and installed at the Untitled Solar Telescope of NSO, where it operated for over 15 years as a facility instrument. She has been a member of the science working group of the DKIST, so the Daniel K. Inouye Solar Telescope, as Rene said, since 2005, and has collaborated on various aspects of the project throughout these years. Since moving to NSO in 2016, she's been working mostly on organizing the community involvement in the scientific exploitation of DKIST. She currently serves as the chair of the Science Review Committee for observing proposals submitted to DKIST. Her main scientific interests reside in the magnetic and dynamical structure of the chromosphere of the sun, including wave dynamics and heating, as well as the physics of flares and small-scale eruptive phenomena. Today, Gianna Kautz will talk about these questions with the perspective of a new look to our star, the sun, with the DKIST, since it will provide the highest resolution solar observations ever achieved, as well as the sensitivity to measure the vector magnetic fields in the chromosphere and in the faint corona. Thank you very much, Gianna, for being with us today. And the board is yours.
Okay. Well, thank you. Thank you very much for this very nice introduction. And I have to thank you for inviting me. It's a pleasure to give this talk. And as we said, I so wish I were there. You know, Granada is a really beautiful place. I've been there several times and I really enjoyed it very much. I had the most terrifying taxi ride of my life in Granada. That was really interesting.
So I forgot to say that this web colloquium is wonderful, but we would like to have you here in person in Granada. Yeah. So I extend the invitation to an in-person one for the future when possible.
Yeah, thank you. Next time. Okay, so let's get down to the presentation. You already heard my name, and I work at the National Solar Observatory. The National Solar Observatory in the US is a national lab, and it is funded indirectly by the NSF. And the charge to the Institute is that of building and operating astronomical facilities that can be used by the national community and also the international community. Some of you might be aware that NSO built and operated the GONG, which is a network of 6 observing stations devoted to helioseismology, and one of them is up on the Teide Observatory. And so today I'm going to talk about the latest and by far largest of the facilities that NSO has built, that is the DKIST, the Daniel K. Inouye Solar Telescope. So this is a fairly recent picture. It's a very big building, as you can see. It's a 4-meter solar telescope. And so the building itself is very high. It's about 35 meters because for daytime observations, you want to put your telescope as far as possible from the ground to limit the turbulence induced by the heat, of course. And it is about 20 meters in diameter here. And it is so large also because it is an off-axis telescope. And I will explain some of this later in the talk. So we are the PI Institute. The funding has been mostly from the NSF. The telescope is built on Aleakala on Maui in the Hawaiian Islands at about 3,000 meters of altitude. It was formerly known as ATST, the Advanced Technology Solar Telescopes, and in 2013 has been rededicated as the Daniel K. Inouye Solar Telescope. Daniel Inouye was a senator of Hawaii in the US Congress. He was there for about 50 years. And he was very instrumental in bringing the astronomy, in developing the astronomy as we know it in the Hawaiian Islands. So after he died in 2012, a lot of facilities in the islands have been renamed after him. Construction started in December of 2012, and currently we have an official closing date of construction as of 15th of November of this year. And when it will operate, it will be the largest solar ground-based telescope by far. The second largest are of the class of 1.5 meters. There is the German Gregor telescope, again, the Teide. And then there is the Phil Goody telescope, the Big Bear Observatory in California. The team is like such. We are the PI Institute, and the director is Thomas Rimmelen. Some of you might know him. And then there are several COAs in the US. And there is a European participation in terms of instrumentation. One of the first light instruments, the VTF, that is Fabry-Perot-based spectral polarimeter, is being built by the Kippenheuer Institute in Germany. And the visible light detectors that are 4x4K that can be read at 30 Hertz have been provided by a consortium of UK universities. And also I need to mention that there is an ongoing collaboration with your own institute for developing a spectral inversion machine much on the, following the footstep of what has been done by your institute for the PHI instrument on solar orbiter. And the PI is Jose Carlos. Okay, so I think I don't know exactly who is my audience today, but I imagine that some of you might ask themselves, why do you need such a large solar telescope to study the sun? And so during my talk, I will try to give you some ideas of science use cases that do require a much larger collecting area. And then at the end, I will present where we stand with the construction and first images and so on. So very briefly, I think that we could divide the major avenues of solar research in three. The sun as a cool star, the sun as a laboratory for plasma physics, and also the sun as the source of space weather. And this is very unique to the sun, and us and ourselves, while the other two are more, astrophysical in general. So during my talk, this is a vast field, and so I will be discussing mostly the atmospheric structure. And the main takeaway, if I'm successful, will be that you believe that in the solar atmosphere, the small scales are crucial and the magnetic fields rule. Really, they are king. And when you put these two things together, you get to my last line that might seem amazing, but the current solar observations, high resolution solar observations, are photon starved. And that is why we need a larger telescope. So we have a common base. Again, I don't know how many of you are solar physicists or not. Let me have a few slides of introduction. So you all know that the sun is a magnetic star, and the magnetic field is really the thread that unifies the atmospheric behavior. Here we have some full disk, some full sun maps of the magnetic field at the surface in the photosphere. that have been acquired by an instrument that's called HMI on board of the Solar Dynamical Observatory. And this is what we call the longitudinal component of the magnetic field. The magnetic field will be a vector, and the longitudinal component is that along the line of sight, right? So during the maximum of activity, you see a lot of magnetic fields, very strong, all these black and white patterns that are the two different polarities. You can, if you have a trained eye, for example, this would be a spot. It's very compact, very round. And so these fields can be of a few thousand Gauss. And they are concentrated in the active region belt. During minimum, 4 years later, you see that the sun is almost fully gray. You know, there doesn't seem to be much. However, one has always to be very aware of resolution. These kind of maps have a spatial resolution of order of about 1,000 kilometers on the surface of the sun. And I remind you that the radius is of order 700,000 kilometers. So if you zoom in, you see that indeed, what seemed almost gray, it's really peppered with a lot of other magnetic structures of smaller scales. These are what we call the network field. And from these maps, we can infer that they have a strength of order of a few hundred Gauss or so. They are actually organized in patterns. I don't know how clear it is for you. There are some semi-roundish cells that we call network cells of sizes about 30,000 kilometers. How do we measure these fields? We have various ways, but the workhorse of our research is really using the Zeeman effect. So you know that in the presence of a magnetic field, transitions levels might split, and so that you have a pattern of spectral intensities that will show you, that betrays the presence of the field. So not only that, so we don't only look for the split of the lines, but we especially look at the pattern of polarization of the light. So we analyze all the Stokes parameters. This is a doublet of iron line that we use very much, and you might recognize these names down here. And so by studying how the intensity and the general Stokes vector, the I, Q, U, and V spectra behave, you can retrieve the magnetic field in the plasma that gave origin to this emission, right? But what I wanted to point out now, because I need it throughout the talk, is the amplitude of these signals. Now, this is all normalized to the continuum intensity. You see here you're around 1 in the intensity, but when you go and look at the circular polarization, this is a semi-quiet area of the sun, but we talk about signals of order of few percent. In the linear polarization, things are even worse, and you are talking about things of order of few per thousand. So this is the magic number, this 10 to the third signal to noise ratio that we need to have in our observations to be able to study magnetic fields in a variety of structures in the solar atmosphere. And actually, you know, this is what we can do now at our semi-diffraction limit. But we would like also to be able to do more. And I'll go through that in my use cases. And then finally, again, to have a common vocabulary, I'm sure you know that the solar atmosphere is usually divided in different pieces that have very different physical properties: the photosphere, the chromosphere, and corona. So if this is the height and 0 is the surface of the sun, and we go up to 1,000, 2,000, 3,000 kilometers or so, and I've put also the sizes in arc second because we often use them interchangeably. The run of the temperature is this in the solid line. So from the surface of about 6,000 Kelvin, you decrease the temperature all the way to about 4,500 Kelvin at a height of about 500 kilometers. And that is expected from an atmosphere in radiative equilibrium. Then something happens, and there is some mechanism to start depositing energy at this height and above. And so the temperature goes up again. And it goes to a value of about 7,000 to 8,000 Kelvin in this stretch that we call the chromosphere. And the temperature doesn't change much there because whatever energy you put into the system is used mostly to ionize hydrogen. Then eventually you run out of hydrogen to ionize around this height. And then so you have, you keep putting energy in the system and you have an explosive heating, and then you get to the 1,000,000-degree typical of coronal temperatures. And the corona, of course, extend much further than these 5 arc seconds or 3,000 kilometers. While the density, these are models, average models in hydrostatic equilibrium. And so the density goes down exponentially, so that the chromosphere is of order 10 to the 4 times less dense than the photosphere. Okay, so let's go to our first science or first and second science use case. And we start from the photosphere. So from the deep part of the atmosphere of the sun. So outside of active regions, the main pattern that you observe on the surface of the sun is that of granulation, which is the manifestation of surface convection. So you have these kind of roundish cells that you can see in this image. This is a continuum about 500 nanometers that are of a size of about 1,000 kilometers. And they are surrounded by these darker lanes, as I hope you can see, that are what we call intergranular lanes. And this is convection. So the brighter things are a bit hotter than the darker one by a few hundred Kelvin. And they are bubbles of hotter plasma that comes up and eventually cools off radiatively, and then expands and precipitates back into the solar surface in the intergranular lanes. So not only the granules are brighter, but they also have an upflow, while the intergranules, that is pretty laminar, while the intergranules have downflows that become fairly turbulent. These things evolve on a time scale of a few minutes, 5, 6, 7 minutes, I think they should go. So I hope you can see the movie. And so we do understand this fairly well. We have theory, we have models, we have simulations, and you might be aware of the work of Asplund et al. In the early 2000s that use these kind of simulations to actually, they apply radiative transfer and they reproduce the synthetic photospheric spectral lines, comparing those to the observations. And the agreement is really outstanding, is the colored, blue and red here, while the green would be what you would be able to obtain with classical models, I say. So everything is nice and good. What happens if we put magnetic field into this system? So here is an example. This is data obtained by the Inouye spectropolarimeter, which is a satellite that you might be familiar with. It's a 50-centimeter telescope. So here are my Stokes parameters that I introduced before. Only now I don't have just one pixel, but I have many. The vertical direction here is the spatial direction of the sun. And by analyzing the polarization, the polarized signal, I can retrieve the magnetic field map, much like I showed you earlier with HMI. So this will be a larger field of view. A large field of view that I'm showing you. The granulation field of view that I just showed in the previous slide will be around this, the size of this little white square here. And so here we see quite a number of things. We see the same network fields that I mentioned earlier from HMI, these more compact and stronger field concentrations here. Surprise, surprise, when you look at it with a much higher resolution, and the resolution of these data is of order of 300 kilometers, so at least 3 times better than what we had with HMI, you see that these fields are not 100 Gauss, but they are more like a kilogauss. So really the strength of the field depends strongly on the kind of resolution that you have. The second thing that needs to be pointed out is that beside the network field, there is magnetic field just about everywhere, right? Smaller scales, peppered black and white just about everywhere. And at least at this resolution, these fields seem to have strength of order of about 100 Gauss. This is the longitudinal component, like I mentioned before. The transverse component you derive of the field, of the vector field, you get from the linear polarization signal. And if you remember my first slide with, the amplitude of the signal, with a signal to noise ratio of order 10 to the third, which is what these data have and what the majority of our data have nowadays, you have an error which is of the order of 100 Gauss, which is of the same amplitude as the strength of your field. So here we are very limited in the kind of information we can get. if we could get a higher signal to noise, what happens? And this is the same kind of data. Of course, it's not the same because that was 5-second exposure and this is 70-second exposure. So you go a factor of 4 higher in your signal to noise ratio. You see that the things change. I wouldn't say dramatically, but they change substantially, really. You have a transverse component, you have a strong linear polarization signal, hence a transverse component of your field just about everywhere, right? So this is one of the the main ideas of having a larger telescope, that you could collect more photons and try to do a polarimetry, more sensitive polarimetry, and go and study these what we call weak internetwork magnetic fields that seem to be present all over the sun. Indeed, there is at least 2 questions that come to mind, right? The first is, what creates all these little magnetic structures throughout the sun? And one of the original ideas was that there would be a sort of side product of the dissipation of active regions. That doesn't seem to work too well as a thing, because there doesn't seem to be any correlation with the solar cycle in terms of how many there are, where they appear, and so on. The other idea is that they are created in situ by a local dynamo. That would use the turbulent motions that are present in the intergranular lanes and some seed magnetic fields. And we will see something in a couple of slides. The other question is, are they important? They are so small, maybe they're not important at all. But again, estimates make it so that this kind of fields seem to bring about to the solar surface about 10 to 100 times more flux than the actual active regions. So they could very well be very important in the overall energy budget of the atmosphere. Of course, we don't know what is their, for example, effect on higher up. Okay, so people have proceeded in studying these fields with better data, better resolutions, and so on. And I like to mention the work of Milan Gozic, that was a student at the IAA a few years ago. So he went and got similar data of much higher spatial resolution. Now we're talking about 100 kilometers. And again, not only you confirm that these things are everywhere, but with this kind of data, you can actually see that they really reside in these small fields really reside in the intergranular lanes only. And that they are brought about by convection. The convective motion of the granulation will shuffle around this field. And let me see if I can play the movie. If you study their evolution, you see that a lot of these little baby structures eventually meet something of an opposite polarity and they disappear, whether they just retract inside the surface of the sun, or whether they undergo some sort of a connection that could liberate some energy to insert into the chromosphere, for example. That is still a very active field of research. Much like before, these data have our magic number signal to noise ratio of order 10 to the third. And if you could do better, you could certainly have a grasp on the transverse field, on the transverse component of this magnetic field that would be necessary also to study whether indeed they undergo a connection or not. So this is my first, let's go. Oh, no, sorry, I went too far. This is my first science use case for a large telescope, right? Have a larger collecting area so that you can push the polarimetry to 10 to the fourth and have a good grasp on the full vector field of these small scale magnetic fields in the quiet sun. Or, the photons are what they are. It's not that you can magically multiply them. You could do the same kind of things that we do today, but at much higher spatial resolution. And that is, and go and check whether a turbulent dynamo really exists, and if it has the properties that some models that we have nowadays predict they will have. So these are just 2 class of models. This is pure MHD. This is actually non-ideal MHD. It takes into account some partial ionization in the photosphere, and they all predict fields maybe with somewhat different strength. But anyway, so that would be a very interesting thing to study. Just briefly, also remaining in the photosphere, that the same kind of new observations with higher sensitivity polarimetry or better spatial resolution will be very useful also to study the fine structure of sunspots. This is an image that I found really amazing. I don't know how well you can see it, but the left side of the image is a simulation and the right side of the image is an observation. So beside marveling how well the simulation worked, what I wanted to point out is the amazing amount of small scale structure that you see that the simulation tell me exists in the sunspot proper that I cannot yet grasp with current observations. And this would be a remnant of probably of convection cells that will be appearing in between very strong field in the spot. So doing polarimetry of these things is still beyond what we can do today. A larger telescope would certainly help in that sense. Okay, so I better get going. Let's move up and let's go to the chromosphere. That is my favorite subject. So the chromosphere is a fairly difficult part of the solar atmosphere to study because it's really a transition region. It goes, you know, you have the photosphere, which is cold and dense and mostly neutral. And then you have to transition to the corona, which is very, very hot, super tenuous and fully ionized. And the chromosphere is in between, right? And so you have all this kind of confusion thing. The chromosphere is also the place where the magnetic field really starts to dominate. You've seen in the photosphere that at least away from active regions, you have that the plasma buffets around the field. And we know that in the corona, the plasma needs to follow the field. In the chromosphere, we are half and half. So we usually use this parameter beta, which is the ratio of the gas pressure to the magnetic pressure. And in the chromosphere, this is the place, because of the low density, this is the place where this thing is around 1. So depending on where you are and when, there will be times when the plasma wins or when the magnetic field wins. And I think this is very well illustrated by this fantastic image of an active region acquired in the core of the calcium-2 8542 angstrom line, which is in the infrared triplet of calcium-2. This is a large area. This is about a quarter of the solar radius. And we have an active region with a spot and all their surrounding things. And what strikes my mind immediately is the presence of these dark elongated features that we call fibrils that really remind me of the filing, the iron filing when you do the experiment with a magnet in high school, right, or in middle school, whatever. So that they seem to evidentiate magnetic field lines, and we think they do, but actually we don't know absolutely for sure, because measuring the magnetic field, the full vector of the magnetic field in the chromosphere is fairly difficult. And I'll get to it at the end. So, and just in case you don't trust me too much, this is the corresponding magnetic map from HMI of the same field. And I go back and forth a few times so that you clearly see that these fibrils seem to originate from strong magnetic field and extend outward. There is a lot to unpack in this image. The chromosphere has been neglected for many, many years because it was too difficult at the end. But since 15 years or so, things have improved substantially. And so now there is a lot of things that we understand fairly well. For example, in this image, you have a lot of little bright things, let me call them little bright things, but they are very different in nature. For example, in this area that you might remember, there isn't much photospheric magnetic field at all. All these tiny dots that have sizes of about 500-700 kilometers or so, they are acoustic shocks. You know that we have pressure waves of the surface of the sun, the P modes, so-called P modes. Some of them can propagate upward, depending on the frequency. They can propagate upward, and then eventually, since the density decreases so much, they steepen and shock. And we know that they heat modestly their surrounding, but they are very intermittent, and they have a periodicity of about 3 minutes or so. And that they certainly are not responsible for the chromospheric heat. Moving up, something here where, where there are stronger magnetic fields, but especially where the magnetic field has an inclination with respect to the vertical, we have a very similar class of phenomena that we call magneto-acoustic shocks, which are the same thing, but the fact that there exists an inclined magnetic field acts as a filter that allow, like a low-pass filter, that allow lower frequency waves, pressure waves, to propagate into the chromosphere. And since those have a higher power, these shocks are more powerful and they liberate more energy again. So there is intense local heating. So this could be a portion of our chromospheric heating, but what we know is that they don't seem to have any effect on the corona. And then we go to this thing where you have not only a strong field, but they're also very tightly packed together. So these are fields that are mostly vertical. They have no room also to expand on the side, right? These are the places that we know are the foot points of coronal loops, very hot coronal loops. But again, why they are heated, we don't know. Of course, the magnetic field is responsible, but is it because of reconnection, or is it because of dissipation of magnetic waves or things? These are still a very active area of research. And it's interesting that these are also the sites where we can observe a phenomenon which has been very popular in solar physics in the last 10, 15 years, again, that we call spicule. And again, I don't know why the movie doesn't go. Let me go this. Okay, so this is a movie again of a chromospheric diagnostics in the UV. And this is looking at the limb. So you might be able to see the limb of the sun here. So I have circled the same things as before. So this would be the acoustic, purely acoustic shock, magneto-acoustic shocks, and this would be those bright things in the dense and packed magnetic field area that we call plage, but seen from the side. And so let's see how clear that is. So you see the acoustic shocks that are very intermittent, a little more strong here in the magnetoacoustic. And here you can probably make out that there is a lot of this very thin and elongated, very long thing that stick up, chromospheric plasma that stick up from the surface of the sun and goes up all the way to, several, many thousands kilometers. This might be more clear in this other movie that has been cleaned and filtered so to delineate only the things that happen at the limb. And so just to have a sense, these are very dynamic things. They evolve on order of a few seconds or so. They're very thin. And here I've put a number. I've put 300 kilometers, but I also say less than, because no matter our resolution, they seem to be smaller, so they're always at our diffraction limit. So whether they have, we really don't know how thin or not they are. They are very tall, so certainly much above the classical idea of a chromosphere. They seem to harbor strong upward motions, so that there is a lot of, current of thought that says that they are jets, probably produced by some sort of reconnection in current sheets that are there, where you have all these vertical magnetic fields that move around against each other. They seem to carry strong galvanic waves, and also they seem to have coronal counterparts. And I've put a question mark here because the resolution, the spatial resolution of current coronal observations is so vastly worse than what we see here that will be, it's actually difficult to find a one-to-one correlation, right? And people have been very interested in them because they seem, if they have a coronal counterpart, not only would they provide energy, but they would also provide mass if they are these flows to the corona, because we need mass up there in order to have a corona at all. Things are still a bit controversial. Some people don't believe that those are flows at all, but they are mostly heating fronts, again, along these current shifts that I mentioned. And I don't know if it is clear, but these are data that have been acquired 1 second cadence with a resolution which is similar to the previous slide. And I think I don't remember which one of these, but if you pay attention to some of these features, you see that some of them appears at once. And that would be obviously incompatible with the idea of an acceleration, right? So that is why the idea of heating fronts is actually, a viable alternative to the idea of jets. But anyway, this is essentially what we know. And also I would remind that we do these very high cadence things, but these are only images because we cannot yet do full spectra of such a large field, so to have a sample of these things with cadences of the order of seconds or a few seconds or so. So this is, well, I will skip this, but I will just put my statement that the case for a large telescope will also be important to study these features at a higher spatial resolution. For now, we know they're less than 300 or 200 kilometers, but I mean, do they keep getting smaller? Which will tell us something really, or what kind of features there might be. And or going and doing spectroscopy at a higher cadence. Of course, this kind of study will vastly benefit from having an idea of what kind of magnetic field gives rise to these features. And here we are, very, very behind because with the famous 10 to the third signal to noise ratio that we can have at the diffraction limit and a cadence of a few seconds nowadays, that is just not enough to measure chromospheric magnetic field. And I think I will skip the actual polarimetry thing because I want to go to the corona, but take my word for it that we really need something of the order of 10 to the fourth signal to noise ratio. So we need many more photons in order to do a proper polarimetry of the vector magnetic field in the chromosphere. Okay, so I'll go to my last science topic, which is the corona that I want to mention because DKIST has a large, a large part of the project is devoted to the corona. So I already said that in the corona, fully ionized, the magnetic field rules because it dictates where the plasma can be or not. So here is an HMI map again, and the corresponding map of a coronal emission in an iron 9 and iron 10 complex, which is around 1 megakelvin to 1 million Kelvin. So you can see a lot of emission where we have strong fields. And also you can see these fainter features that we call coronal loops that really follow the magnetic field. The magnetic field of the corona determines the heliosphere status and so on, and we are essentially blind to it nowadays. Again, because you can imagine as you go away from the surface, you have, the field decreases. So it gets from 1,000 Gauss, you go down to 10 Gauss or something like that. So measuring it becomes very, very difficult. And also the corona emits doesn't emit much, it's a very tenuous plasma. By the way, most of the information that we have nowadays from the corona comes from UV observations from satellites, like SDO, and that they have no polarimetry and a much coarser spatial resolution than what I've shown until now. The spatial resolution of these images of the order of 1,000 kilometers or more. If you do spectroscopy, UV spectroscopy, that goes further to 2,000-3,000 kilometer resolution or so, because you don't have light really, and so you have to integrate a lot. But anyway, so we know very little of the coronal magnetic field. We have been using a lot of extrapolations. So you take the boundary condition, you take the field of the photosphere, and you extrapolate it upward with some set of assumptions. For example, you can do potential extrapolation, or you can go a little more sophisticated and allow currents in the system, but only along the field lines and what are called force-free field extrapolation and so on. And we compare them to the plasma features that we see, to the intensity features that we see. We have very little measurements of the magnetic field to compare this extrapolation with. In a sense, this is a bit of the holy grail of current solar physics, to go and study the coronal magnetic field. So much so that I think in the last literally few years, there have been a flourish of ideas and techniques that do not use polarimetry necessarily, So here I've put a collage of very recent works. They're all from last year. So in this case, we have a full disk. You can see it here observed with a chronograph so that you kill the disk emission. And you study the emission of some lines at a little distance from the disk itself. So by studying waves in intensity and velocity and their properties via models, you can go back to the kind of field that will allow these waves to behave as they do. And here they have, you can see the scale here, that you have fields that go from very little to about 4 Gauss, which is a number that has been mentioned many, many times in order of magnetic fields. Now, these are, these are general structure, broad coarse resolution. There aren't obvious active regions here. This is instead using synchrotron emissions from, from radio measurements. And actually, I don't know if they use polarimetry here. I'm not 100% sure. This will be an active region because they're looking at flares, but still, I don't know if you can see it here. There is the limb, so this is off limb, but they find fields of order of several hundred Gauss. So there is quite the difference between these. So is it a matter of being an active region versus quiet, or is it a matter of having a better resolution, or so on? That is, to be studied, TBD. And this one is very, very neat idea. This is something that I still don't understand very well, but apparently there is, by virtue of some strange quantum mechanics mechanism, in the presence of the magnetic field, of a magnetic field, there is a transition of iron-10 that appears that wouldn't be there otherwise. And this has been observed by chance several times with this UV spectrograph. And so by studying that transition in active regions, Landi et al. Last year managed to give us the magnetic field map of a full active region. As you can see, this is the intensity and this will be the field. And again, we see that the numbers are actually much, much higher than what maybe we were expecting. So this is a very much work in progress. And DKIST will like to enter this debate and fray by using polarimetry. So there is a lot, not a lot, there are several visible and infrared lines that can be used for doing coronal polarimetry. They are forbidden lines, so they are excited in a different, way than the UV lines. In particular, they have a component, the levels are excited also by radiation that comes from the disk, of course. The UV continuum is of the disk is about 0, but of course the infrared continuum, the visible and infrared continuum of the disk is large. This is bad and good. It's bad because the formation of the lines is more complex and you have to, to be careful about that. But it's also good because the component due to radiation is proportional to density and you can see structures much further away from the disk. The UV structures will be visible only, at a lower distance, at a smaller distance from the disk than the visible coronal structures. As an example, this is an eclipse with a white light. This is just Thomson scattering of the photospheric continuum, a lot of fine structure. And these are spectroscopic data of the same eclipse in iron 11 and iron 13. Here, this is 11, I got it wrong. So they are visible. And they are actually sensitive to the presence of magnetic field. And actually, you could measure the strength of the field along the line of sight by via the Zeeman effect. So measuring the circular polarization of the light. There is only a little problem, is that the typical emission of these lines are of the order 10 to the -4 of the disk intensity. So that is, you can imagine why you might need a very large telescope to start studying this. Now, I am optimist, and I say that 10 to the -4 is what we know nowadays, but it's also true that nowadays the coronal observations from the ground have been taken with very low spatial resolution, right? So if we manage to get a much higher spatial resolution, much like the case of the field, we might be pleasantly surprised, and the actual intensity of the single structures might be larger than this. So we might have a little easier life. I will skip this slide. So there are, I already mentioned, there are several lines that could be used to do polarimetry. The most plausible candidates are a doublet of iron 13 around 1 micron, and then silicon 9 at around 4 micron. And DKIST will be able to go to these wavelengths. There are coronal lines further in the visible, for example, the famous green line at around 500 nanometers, that are even stronger. But the question is that the sky is much brighter at those wavelengths. So the scattered light in the atmosphere goes with wavelength, the inverse of wavelength. So going towards the infrared, that becomes a better bet in order to get a good signal. Of course, we will not do diffraction limit in a few seconds with 10 to the 4th. That will not happen. Just to give you a sense of where we stand, this is an observation, one of the very few observations of this kind of data that we have nowadays. These were taken with a coronagraph on Haleakala, but the coronagraph was less than half a meter of a telescope. So here we have 10 panels that go from closer to the disk to further from the disk. So 0.1 solar radii and 0.28 solar radii. So the Gaussian-shaped curves are the intensity observed in iron 13, and the wiggly, noisy thing are the circular polarization. And you might be able to see, it's not a great figure, but there is also a fit with a typical Stokes V profile, that would be the one that gives you the intensity of the field. Right. So this is the kind of thing that we have until now, and they had to expose forever and have super big pixels of order of, light. So DKIST hopes to do these kind of observations in a much less time, and hopefully also with higher spatial resolution. Okay, I think this is. Sorry, this is the end of my use cases, and I hope I convinced you that we could really use a larger telescope, and especially one that can do polarimetry and do it well. And so now I have a few slides on the telescope itself, and then I will have some first images. This is a cutout of the building that I've showed you earlier. This is the telescope assembly. There will be relay optics at this level, and then the light is sent down vertically to this rotating platform, Coude platform, where all the instruments reside. The instruments are here and they are fixed; they don't move ever. This is very typical of solar observations. Here in red, I don't want to go through them all, but I have put what I consider to be the most important features of the telescope. And actually, I think in the next slide, I have highlighted them differently. So this is a 4-meter diameter. And that has been what I've been talking about until now, how to use your enhanced collecting area. This will be at least 10 times more light that we have, collecting area than we have with the largest telescopes today. So you could do ultra high spatial resolution, and the diffraction limit is less than 20 kilometers on the surface of the sun at 400 nanometers, or you can use the telescope as a light bucket. And the light bucket will allow you to do things that we do today with a much higher cadence, or with a much higher precision polarimetry. And that is our goal, right? We have the magic number that today is 10 to the 3, and we wish to get to 10 to the 4. The telescope is all reflective, and this allows us to go all the way to the thermal infrared, so about 28 microns, although currently the first light instrumentation is limited at 5 microns. The telescope is an off-axis, and which is also the reason why the dome is so big. If it were an on-axis, it could be much narrower, but it's off-axis. And one of the main reasons of the off-axis design was to avoid the spider and the central obscuration, and that have consequences both on the spatial resolution and on the scattered light. The scattered light is a big thing because we want to do corona, and I've told you the kind of intensities that we want to get. Yeah, I think I didn't mention it, but we often measure the sky brightness in millions of the solar disk, and a normal sky brightness is of the order of at least 50 to 100 millions. So that will be already at the level of the signal that we expect from coronal structures, although I personally hope that will be better. So you have to kill that kind of signal. And that is also why the mirror, the primary mirror, is highly polished. And there is a lot of systems in place to keep it clean, from water washing and CO2 washing and so on, and also recoating facilities, which is next door. The coronal science use case is also the main reason why the telescope is on Haleakala, because Haleakala is very well known as a very dark coronal sky place from site service and so on. And finally, it will be a multi-instrument telescope in the sense that not only it's got many instruments, but most of these instruments can also work together so that you can have a multi-wavelength or a multi-topic approach to the kind of science that you want to do. So this is just a quick drawing of how the light goes. So you have the incoming light here, the mirror. It's an off-axis, so it's an f2, so about 8 meters there is prime focus, and shortly after there is m2 that it is about 90 centimeters, I think. And here in the prime focus is where you put your heat stop. You might imagine that having a 4-meter telescope looking at the sun will create a lot of heat that you have to manage. Indeed, not only the dome is thermally controlled, the actual, only a small portion of the solar light actually goes to M2 and then the instruments, and the rest is rejected by this so-called heat stop. Then there is a complex system, hardware system here of absorbers and pipes of coolant to keep that environment at stable temperature within, ambient temperature. So then in the secondary focus here, the Gregorian focus, we have the limb occulters if you want to do corona studies. So you have to kill the disk, of course, and the polarization calibration, which is a major part. I mean, I would say that this is almost like another instrument. And then finally, you relay the light to the Coude platform. The Coude platform looks like so. So it's about 16 meters in diameter, and it hosts 5 instruments that are here very quickly depicted. So let's see if I can describe them in some detail. So the VISP is a classical spectrograph, slit spectrograph that will do polarimetry. All the instruments do polarimetry apart from this. So this is a classical spectrograph. This is an imager. Broadband filters. This has been thought as the camera of the telescope, right? It's the one that will produce the best diffraction limit images and the highest cadence. This doesn't have any spectroscopic capabilities, really. It's just broadband and doesn't do polarimetry. Then we have the DL-NIRSP, which is again a spectrograph that will work mostly in the infrared from 1 micron onward. And it's an IFU using fibers. So here you will be able to have both the spectral and spatial information at once. Of course, nothing is free in light, and so you will pay that with a fairly small field of view that you can observe at once. The VTF is a German instrument. It's a double Fabry-Perot-based spectral imager and polarimeter, indivisible. And finally, you have the cryo-NIRSP, which will be the coronal instrument par excellence. So it will work in the infrared all the way to 5 microns, and it's cryogenic in order to kill noise as much as possible. As you have seen, the coronal observations are fairly delicate observations. And here I think that I have put the images. Let's see, this is the VBI, corresponding to the position, more or less. This is important. This is the adaptive optics system. Of course, if you want to do diffraction limit with a 4 meter, you do need an AO system. And this is a high order. It's got 1,600 actuators. And there is actually work in progress for a multi-conjugate system that will come in the next few years. These four instruments can work together by splitting the light. And that means that you split the wavelengths, really. All of the light at any given wavelength go to one instrument. And then with beam splitter, the redder light goes to another, and the redder goes to another, and so on. The cryo will work alone. The coronal one will work alone. This I will skip. And then I'll go with nice pictures. So this is the building very recently. These are the Palm Stars telescope, if you're familiar with. So you see it's a big thing. And this is the Air Force facility. The DKIST is just at the edge of the mountain because that is where the best daytime seeing conditions were found to be on the site. This is recently they were doing an on-sun campaign, and so you can see the dome doesn't open completely, just the aperture for the beam for the primary mirror, and the dome is actively thermally controlled. And then this is just for fun because the person that took this picture claimed that there is no filters applied, and this is around noon, and this is the color of the sky. So you understand why Haleakala has one of the best coronal skies in the world. The telescope, I'm sure you've seen many in your lifetime, and so just a scale, these are two people. And here is the assembly with the heat rejector, and this is the secondary. The heat rejector here was a preliminary version. I think that now they have a different system. From the back, M1, as I mentioned before, needs to be kept clean and needs to be recoated maybe more often than others. So the Air Force facility has a coating chamber, which has actually been enlarged just because of DKIST. So that is where the mirror is taken when it needs to be recoated. And this was, I think, about a year ago was the last time that was done. The CUDE lab, it starts to be crowded by now. So all the instruments are on site apart from the German one. And some of them have undergone science verification. Some are doing it as we speak. So here, I think I wanted to put this picture because we were talking about before. This is the science verification test of the VISP. And here is Roberto Casini, that you all know as the PI of VISP, and Alfred Deven is project scientist. And here we have some polarized light image on the screen, right, as taken from the VISP. I don't have anything that I can really show you about that. So the AO, it's an instrument in itself. It works at 2000 hertz, and so you can imagine it's a fairly complicated enterprise. And then finally, because I'm super long as usual, some first light images. So this was the first light last year. Was taken in the red continuum at about 800 nanometers, and that the nominal resolution of that wavelength is of the order of 30 kilometers on the sun. So this is about 35, the size of a supergranular cells of a network cell, as I mentioned very early in the talk. And you might say, well, I think you showed me this before, right? When you have that movie that looked fairly similar. This is true, but now I can zoom in, for example, and go and look at the details in between, in the granules, but especially in between the granules, where we know, or we think we know, that all the magnetic fields are swept. And I think it's a very fantastic image that you see, not only that there are these bright things that, again, we correlate with magnetic fields, but they can be extremely small. I mean, we're talking about a few pixels here, and also have these very convoluted shapes that probably depend on the kind of turbulent flows that you find in the intergranular planes. So we don't have polarimetry of these things yet, unfortunately. A movie about how they evolve, and I think the movie has a bit of a stop and go that it repeats itself at some point. So, but it's a few minutes movie, so you see how the convective motion sweep these elements that, again, we think are magnetic elements. and how they carry and stretch and so on. The first image of a sunspot, this was taken actually not with an instrument per se, it was taken with the camera of the AAO system at 500 nanometers. And again, I don't know, maybe we can discuss this in the comments. The amount of details is staggering, and you start seeing, maybe because it's a small sunspot, but you start seeing a lot of these details inside the umbra proper that were in my simulation image. And the last one, this is fairly recent. This is the first image in the blue continuum. Now we're talking 450 nanometers. And the diffraction limit is of the order of 16 kilometers. And there's a small active region with, and I am actually very curious about these kind of features that have all these spikes that come out. Are they baby spot in the making or something? So again, I don't have, for example, evolution of this one, but here there's a detail, you know, like something inside the intergranules. And is that really like a baby spot, or is it a hole? I don't know. So thanks for your attention. I'm always too long. And I leave you with a couple of papers and the website that you can consult to for your, you know, if you want to know more. Thank you.
Thank you very much, Jana. It's been a very enlightening talk, and well, at least I enjoyed it very much. I hope it has been the same for all the attendants. So the floor is open for whoever wants to ask Jana.
Yeah. Was convincing.
Oh.
Yeah,
Isabel, Isabel has his hand raised.
Jana, excellent talk. I enjoyed it a lot, really. It was very clear, and yes, now I'm excited about the possibilities of this telescope. Can you tell us a bit more about the science verification phase? How is it going? Which instruments are already more or less operational?
Well, you have seen images from the VBI. You know well, the VBI was always meant to be the first thing to come online because it's the one that can tell you whether the telescope works or not, right? And so let's see, full disclosure here. When we show these beautiful images at the diffraction limit, they have been acquired by making full use of the AAO system, but of course there is a lot of post-processing as well. You know, we go and do what we call image reconstruction. And so for now, that has been applied to these images to reach the diffraction limit, and it works. We don't know yet whether, you know, the seeing is stable enough to have like long sequences of these things, because this is what we really want, right? To have extended sequences of that. So for now, we have some burst of that, and so, but I mean, the VBI works, the filters work. Apparently, I haven't seen yet an H-beta. I'm waiting on that. And the science verification for the VBI has been completed. The VISP had their science verification period in April, May. So, and they're working on the data right now. Let me get it right here. I think that the cryo-NIRSP is doing it now.
Okay.
Is doing it now, and the DL-NIRSP will be doing it just towards the end of the construction phase. So we're talking about November. I think they have what they call the on-sun campaign, when they actually use the time for these kind of things that are interspersed with more technical things that still need to be done in the telescope. But so the idea is that by November 15th, all instruments will have undergone science verification. And the VTF not. The VTF is not physically there yet. The VTF should be there next spring, as far as I know.
but it's quite impressive because what you have achieved during the pandemic is really amazing. I mean, so difficult.
Yeah, there have been 3 months. They stopped for 3 months. Then they started going in, reduced number of people up, all precautions and so on. They are still in that mode, although it was relaxed. You've seen there were several people in that room, right? Now, unfortunately, Hawaii is going up again with cases, and I don't know how that will impact the rest. But overall, I mean, if you ask me, building a telescope of this kind in less than 10 years is a miracle. There was, they literally started groundbreaking in December 2012. So yes, I think it's a lot.
Very good luck for this later, this phase, the last phase.
Yeah. Oh yeah, there is many more things to do, right?
Yeah.
Okay. I think there was Isabel then.
So
yes.
I think.
Yeah. Yes. I was just.
Isabel?
Yes. Can you hear me?
Yes.
Yeah.
Okay. So I just wanted to, I mean, it's not just to pose questions, it's just to congratulate you, Gianna. It has been an excellent talk.
Thank you.
Very informative and with exciting science and perspectives. I already told you that I'm from the extragalactic field, so galaxies and so on, and I found it, I'm really grateful for the level you've given to the talk, because I think it's been, great.
You were my target, right? You were my target.
So thank you. That's what I wanted to say, that I thank you very much for such a great talk.
Thank you.
Congratulations for the huge work that is behind.
Oh yeah, it's not me. It's a lot of other people.
Yeah, so it's a team.
Of course, yeah. No, I didn't do much. I mean, I just go and give talks, right? Yeah.
Great, thanks a lot, and I insist on inviting you for the future when you read. I mean, it'll be great to have you here. Thanks.
Okay, thank you, Rene.
Yeah, thank you. I have a question, but it's not from me. As you know, we are live in YouTube, and a person called David Orozco.
Oh,
he wants to ask a question.
Is he on the beach or something?
I don't know. The question is, first he say, okay, congratulations for the speaker and all the team. And the question is, for the coronal observation, how much close to the limb of the sun do you expect to have useful polarimetric observations in emission coronal lines?
The goal is to have it very, very close. We're talking about a few arc seconds above the limb. That is the capability of the occulter. So you can over-occult and under-occult, but I think that the minimum will be about 5 arc seconds, which is 3,000 kilometers or so. So very, very low. The hope is that everything works well, right? Because the scatter light there would be a killer, really, if you had something leaking from the disk. But very low. I think I didn't say it, but the maximum that you can point to the telescope, because after that there are mechanical issues, you can go only 0.5 solar radii away from the limb. That's the maximum, but the minimum is really very few thousand kilometers. Yeah. So one thing, I mean, I talked about the polarimetry, but certainly, doing imaging of the corona and high resolution together, because the VBI can do that. You can observe a coronal line with a filter, with a broadband filter, and the chromospheric line, for example, H beta, at the same time, or calcium 2 at the same time. That would be extremely interesting in itself without even touching polarimetry.
Yeah. And any more questions? Well, I certainly have several, but I wanted to ask you about the adaptive optics system. So how is it working right now? Is it still fully operational? Which are the periods with stability and the requirements? you expect to reach?
Oof. I'm not sure I fully understand the question. The system is working well. It's working at 2 kilohertz, right? And they have these 1600 actuators, a little less, I don't remember the exact number. It is a single layer, you know, AO in a sense, is classical in that sense. I don't know exactly what kind of requirements you had in mind. How long it can work for, say for an hour or 10 hours or forever.
Instance, yeah.
I don't know, actually. I cannot answer that question. I'm sorry. But I will investigate it. Yeah.
No, well, I'm puzzled by evolutionary studies that we gathered, sunrise, for instance, and the wealth of information you get when you see parametric movies is tremendous. So
yeah, no, I understand, and I
really waiting for having those movies from
right. So the site survey gave information on the actual seeing properties of the site, and they had extended periods of very, very good seeing overall the year. Now, you know, that was taken more than 15 years ago. Whether, unfortunately, we all know that climate is changing sensibly. And for example, at Sac Peak, they did notice quite a variation of the seeing characteristics with respect to what everybody remembered as the standard, right? So what that means at Haleakala for daytime observations, I don't think we can properly say at the moment. So I still hope there will be very good sequences, but as you know, I mean, these are not every day. You know, they happen. This might be a surprise to our nighttime colleagues, but really, much of the science that we do is done on a relatively small subset of observations, the ones that are acquired with the best weather conditions, right? Because the mediocre conditions, we've got so many of them. Really, they don't, in a sense, they don't tell us too much, and especially from the ground, they often don't have consistent quality, right? If it was always the same, you could do a long study and so on, but today is like so, and tomorrow is a little less, and then this changes. And so
within a day, which are the daily variations of seeing?
So the best seeing, very good, is early in the morning, very early in the morning. And so on. And that was originally thought, you know, from the results of the site survey, that the high resolution observations would be performed in the morning, and then you would switch around noon and afternoon to coronal data, right? Because there, you cannot do point or whatever arc seconds, right? Because you've got no light, so you still have to integrate it. So you would exploit those lower seeing quality times, and also at noon the coronal sky is the best. So that was the original plan. Then how easy that is, in principle, it is easy to switch instrument, and easy enough. But of course, you can do that when you are at a certain level of confidence in how you can operate the whole thing, do the calibrations and so on. Sorry, I have a machine outside my window. I don't know if you hear it.
So Renee, again, you have...
Thank you. There is another question in the chat. Astronautico asks you, are you working with the Solar Parker Space Probe team or data from the spacecraft as a method to confirm the data or to compare?
So several answers. I personally am not. Many of our colleagues are actively using Parker Solar Probe data for other kinds of studies. Parker Solar Probe is an in-situ instrument, so they measure things in the heliospheric environment of the sun, right? And most of what I've said today was referred to the actual sources at the sun in the solar atmosphere. There is quite a bit of collaboration around, and not me personally, that to put the two together to see what happens at the sun and then what the probe measures in situ at a given time in a certain position. And certainly we have plans, you know, DKIST still does not observe, we're still constructing, but we do have plans to perform coordinated campaigns to address this kind of problems, right? Study at the same time the source and the effect in the heliosphere, both with Parker Solar Probe and also Solar Orbiter.
So,
okay, Jose Carlos, I think it's okay for ending the talk here.
Yeah, if there are no more questions, we can close. And well, before closing, I would like to thank again Jana for her kindness in giving the talk, in preparing a talk for a wide audience, and for being kind enough as for citing the work of our colleagues here in the institute. It is very much appreciated. I should say that one of our last professional interchange was a kind scolding by her on my paper, who had forgotten to cite some of her work and her team. So I really appreciate her citing IAA's work, which indeed is interesting and well. I would also say that we are aiming to be as less delayed as possible to deliver the inversion factory, which is was expected to be delivered last year, and due to the pandemic, we are even more delayed than you guys. So excuse us.
I'm still surprised that we work. I mean,
Yeah.
I'm done. I'm just like, I'm tired. So in these conditions, you know, it's difficult. So.
Thank you.
But anyway, no, I mean, IAA and you guys are the leaders, the world leaders of these quite some fields, right? So, of course, I cited you.
So,
Okay.
thank you, and hasta la próxima.
Hasta la próxima, hasta presto. Pronto. I think I might check in your meeting in Göttingen, but okay. I hope to be on the beach on those days, so I don't know. We'll see.
We'll see.
You are more